To find more complex life, we need to fast forward to 3.5 billion years ago. And a shallow ocean. These look like rocks, or even plants, growing out of the seabed. Each mound is a colony of living bacteria called a stromatolite. These bacteria turn sunlight into food, a process called photosynthesis. It uses the power of sunlight to transform carbon dioxide and water into glucose, a simple form of sugar. And this magical transformation releases a byproduct, a gas called oxygen. Underwater, the stromatolites slowly fill the oceans with oxygen. The oxygen then turns traces of iron into rust, which fall to the ocean floor to form deposits of iron-rich rock. It's this mineral that will one day be used to build bridges, ships, and skyscrapers. Above the waves, the oxygen transforms the atmosphere. These stromatolites are creating the most important element for life on Earth. Without them, virtually every living thing wouldn't exist. Over the next 2 billion years, oxygen levels continue to rise. And as the planet's spin slows, the days get longer, lasting at least 16 hours. Three billion years after the planet's birth, there's still no complex life. No plants, no dinosaurs, no humans. But the Earth has something unlike any other planet in this solar system. A force with the power to change everything. $1.5 billion years ago, the Earth is a beautiful blue ball, dotted with volcanic islands. Over millions of years, a mysterious force rearranges these islands. Hidden beneath the ocean, the Earth's crust breaks plates. But even deeper, the Earth's core is so hot that it generates movement in the rock beneath. These movements push and pull the plates around the globe, carrying the oceans and islands with them. Millions of years race by. Our planet is alive and changing. Over 400 million years, a vast new supercontinent takes shape. It's called Rodinia. In the shallow waters surrounding Rodinia, stromatolites work their magic for more than 2 billion years, pumping oxygen into the atmosphere. Temperature is 85 degrees, and the days are 18 hours long. But this planet looks more like Mars than Earth. To find life, we must fast forward through time. Walton State, 750 million years ago. A force deep inside the planet rips the crust to pieces. It's as though the world is breaking apart. And there's only one force powerful enough to do this: heat. It escapes from the Earth's molten core, stretching and weakening the crust. Inch by inch, year by year, the great supercontinent is splitting in two. The intense geological activity spawns a mass of volcanoes. They pump carbon dioxide into the atmosphere. The carbon dioxide mixes with water and creates acid rain. When the continent tore apart, many rocks were exposed. These rocks absorbed the acid rain, including its carbon dioxide. Vast quantities of CO2 are absorbed out of the atmosphere. Now, there's not enough carbon dioxide in the air to trap the sun's heat around the planet. In just a few thousand years, the temperature plummets to around -60 degrees. This frozen wasteland is southern Australia, 650 million years ago. It's the start of what some scientists call Snowball Earth, a period they believe to be the longest, coldest ice age ever to grip the planet. A vast wall of ice looms thousands of feet high. And it's unstoppable. The more ice there is, the more sunlight it reflects away from the planet, and the faster the ice spreads. Nearby is a second ice sheet, just as high. The two sheets spread away from the poles toward each other to meet at the equator. Now, an ice sheet up to 10,000 feet thick covers the entire planet. Earth first began as a molten ball of fire. Now it's a frozen ball of ice. Virtually all the sun's light and warmth reflects back into space. And it seems as though nothing, Not even the sun can rescue the planet now. $650 million years ago, ice entombs the planet. For 15 million years, the Earth is a vast frozen snowball. But it can't last forever. Something must release the Earth from this frozen prison. And when it does, who knows whether life has survived beneath the ice? The surface is frozen, but the core is still hotter than the sun's surface. Volcanoes have been erupting since the world began to freeze. But up until now, even their heat and power made no impact on the ice. Volcanoes pump out billions of tons of carbon dioxide. Before the Big Freeze, the Earth's rocks absorbed most of the CO2. But now, with the rocks smothered in ice, there's nothing to absorb the gas, so it fills the atmosphere. Like a blanket, it traps the sun's warmth around the planet, allowing the temperatures to rise. Now, after 15 million years, the ice begins to melt. It's thought that during Snowball Earth, the ice pushed the crust down. But now, as it melts, the crust bounces up, creating fissures and weak spots, and more volcanoes. The volcanoes release more carbon dioxide and push the temperature up even higher. The melt gathers momentum, and oxygen levels rise. Through a series of chemical reactions, the ice has created oxygen. While the planet was frozen, the sun's ultraviolet rays reacted with water molecules in the ice to produce hydrogen peroxide, a chemical rich in oxygen. Now, as the ice melts, the hydrogen peroxide breaks down and releases massive amounts of oxygen. The Earth is waking up, and it's a very different place. $600 million years ago, the atmosphere is warmer, like a summer day. And the days are about 22 hours long. Add all this water, and it's the perfect recipe for life. Before Snowball Earth, primitive bacteria emerged in the oceans. But surely they couldn't have survived an ice age 75 times longer than the entire span of human history. If something has survived, then life may be found where it was last seen, in the oceans. Now, 540 million years ago, in an ocean full of oxygen, those